Let us now work on some examples related to hydraulic power, and let us see what is the hydraulic power of some common water pumping applications and arrangements. So let us first take an example, a very common example. This can be considered as a household example in most of the homes in the country. You will have a sump, and from the underground sump you will try to lift water. This is the suction pipe, and let me put a centrifugal pump, and most of the homes will be having a single phase centrifugal pump. The delivery pipe will travel quite some distance horizontally, and then up again to deliver to a overhead tank, because the overhead tank may be placed at quite some distance from the pump and the sump. So let us indicate some water in the sump, and the suction pipe is going almost to the bottom of the sump tank, and the water is discharged in the overhead tank like this. Now, what is the suction head? Suction head is from the tip of the delivery pipe to the center of the axis of the pump. So let us mark that, and I will mark that one as HS. This is the suction head. What is the delivery head? From the center of the pump axis up to the highest point that the water reaches up from the horizontal would be the delivery head, HD. Okay, that is not all. You see, in most of these kind of applications, the overhead tank may be in one corner of the building and the sump may be in another corner of the building, and then there is quite a distance of horizontal travel where actually there is no physical head, water is not lifted, but there is quite a significant amount of friction loss due to the horizontal travel. So let us also indicate what is this total horizontal distance that the water is flowing. So let me mark that. So this is around, let us say, 120 feet, which is pretty common in most of the homes, traveling horizontally around 120 feet. Now let us say this height, the suction head pump height, is around 6 feet deep into the sump tank, and then going up close to 2 floors would be 20 feet delivery head. Now let us talk about the pipe diameter. Most of the homes in recent times use pipe diameter of 1 inch, again depending upon the number of people in the household, and mostly PVC pipes are used. So recall that for PVC pipes, the surface is very smooth, the inner surface. The surface bumps are negligible, and therefore the roughness ratio is 0. So that is an advantage. So let us put down some specs for which we can calculate the hydraulic power. First is Q, discharge volume. So the discharge volume would most of the time would be the size of the overhead tank. Now let us say you have a 1000 liter tank. So let us say we want 1000 liters, and this 1000 liters, how soon do you like it to be filled up? Most of the pumps in our homes will be able to fill up this in 10 minutes time. So I will just put in some time here. The discharge time, delta T, is 10 minutes. So actually Q dot works out to be 100 liters, 1000 liters by 10 minutes, which is 100 liters per minute. That is the discharge rate or the flow rate. Now if you want to convert it into meter cube per second, so you have 100 liters by 1000 to convert it into meter cube by 60 seconds. So you'll have 0.001667 meter cube per second. So you have the discharge rate in meter cube per second. What is the diameter? Diameter given is 1 inch. We need to convert it into SI units. So 1 inch into is 25.4 mm. Mm to meter is 25.4 by 1000. 1000 mm is 1 meter. So you can convert inch to meter by multiplying by a factor of 25.4 by 1000. Suction head is 6 feet. Converting the feet to meter, 6 feet contains 12 inches. Each inch is 25.4 by 1000. So that is how you convert it to meter. Let me make some space. Then the delivery head, 20 feet, 20 into 12 into 25.4 by 1000 in meter, because each feet contains 12 inches and each of that inch contains 25.4 mm by 1000, and therefore the conversion to meters. Now the total length of the pipe. So the total length of the pipe is needed because we need to calculate the loss due to friction. So it is not sufficient you just take only the suction head length and the delivery head length. You should also take all the horizontal portions of the pipe too, because they contribute to the friction loss, and in fact they contribute a significant portion, because 120 feet is not small, it is much larger compared to the heads. So therefore 120 feet plus 20 feet plus 6 feet, 146 feet is the total pipe length water has to travel through, and there is going to be friction loss in this much amount of the length. So convert that one into meters, 12 into 25.4. So this will be the meters. And you can also now find the area pi by 4 d square. Now next, find the fluid velocity of the water in the pipe, U, in meters per second. Now we know the discharge rate, this is meter cube per second. Now this volume of water is flowing through the pipe every second, so much meter cube is flowing through the pipe every second, and that pipe is having a cross section area A, and you could divide by that A to obtain meters per second the velocity of the fluid. So therefore Q dot divide by A, this is meter cube per second, this is meter square, therefore you will get it in meters per second. So this will turn out to be, if I use Q dot value which we have calculated and A value here calculated using the D value, you will get 0.001667 meter cube per second for Q dot divided by A, which is pi by 4 d square, which is in meters square. Whole thing, when you calculate and substitute the value of d as we found out here, it will come out to be 3.3 meter per second. Next, let us find the Reynolds number, which is given by UD by nu. So 3.3 meter per second into d, which is 0.0254 meters, divided by nu, which is 1 into 10 to the power of minus 6 meter square per second. So this Reynolds number, we have used this term nu, which is the kinematic viscosity. This kinematic viscosity for water is a function of temperature. For different temperatures you have different viscosity. So for water at 20 degrees centigrade, you can look into the science tables. You will see that it is around 1.004. I approximately put it at around 1 into 10 to the power of minus 6 meter square per second, and when you apply these results and calculate, you will get 83820. So 83,820, much larger than 4,000. So the flow is turbulent. You have to use the Colebrook-White formula for this. We have already done that exercise and have the function for that in Octave. You can use that function readily. So before that, calculate the roughness ratio. Epsilon, which is the height of the surface bump for PVC, is 0, and therefore epsilon by d, the roughness ratio, is 0. And now you can find out the friction factor first using the Colebrook formula. 8 Reynolds number you have to provide 83820 and the roughness ratio, which is 0. So for that, when you run the Colebrook's iterative algorithm, you will land up with 0.018683. Now that is the friction factor. Now using that friction factor, we have to calculate what is the head loss due to friction, and for that we will use the Darcy-Weisbach formula. F into L by diameter, inner diameter, U square by 2G. So if you substitute the values, you will get 18.05 meter. Now what is the total dynamic head, H? Now this is 6 feet of suction head converted to meter using this factor, 12 into 25.4 by 1000, plus 20 feet of delivery head, 12 into 25.4 by 1000, plus 18.05 meter of the friction head loss. So if we calculate this, you will see that it is around 25.97 meters, which is approximately 26 meters. Compare this 26 meter of total dynamic head loss, 18.05 meter is contributed only by friction loss. So it is not just sufficient for you to calculate the power based on only the height difference. The horizontal flow of water in the pipe also causes significant pressure loss, and you have to account for that, otherwise your pump power will not be sufficient to pump the required amount of water, the required time to the required height. So what is the hydraulic power? 1000 into 9.81 rho g q dot h, q dot into h, watts. So 1000 into 9.81 into q dot 0.001667 meter cube per second, all in SI units. H, the total dynamic head H is 26 meter, we just calculated. So this all comes to around 425 watts. So 425 watts of hydraulic power, worst case, is needed for pumping water from the sump to the overhead tank, which is 20 feet above the ground level. You will need 425 watts. So probably most of the homes will have a 1 HP single phase pump to do the job. Let us now work on example 2. This example 2 apparently looks exactly like example 1. It is the same system, all parameters are the same except a small modification. I will mention what that modification is, and you can see a lot of things that you can achieve by that. We will go for a solar photovoltaic solution. So it's a solar based solution. We want to use the sun power, and this pump is driven by a motor, and that motor is not actually powered from the mains, 230 mains, as in the earlier case when we said that probably a single phase motor will be driving this pump. Let the motor which is driving this pump be a DC motor, and let it be directly connected to the PV modules. Let there not be even a battery. You will see that the solution is so much more advantageous, because instead of storing it as chemical energy in the battery, we can store it as water at a lifted potential, pumped hydro. So consider a typical household, the requirement of total discharge volume of, let us say, 1000 liters in a day. So if, let us say, the household is requiring 1000 liters in a day, instead of putting a 1000-liter tank, you put 2000-liter tank. So let us say this tank is 2000-liter capacity. Now fill up this tank for complete 2000 liters. So in a day, 1000 liter is utilized by the household, 1000 liter should be put back into the tank by the end of the day. So that is the logic that we will be using. So delta T, instead of 10 minutes in the example 1 case, we will link it to the insolation at the place. So we know how to find out the insolation at the place. So if I plot the insolation versus time, it looks something like this, and this is the peak is occurring at noon, and the area under that curve is kilowatt hours per meter square per day. Insolation is kilowatt per meter square. Now this is equivalent to saying the HAT, the insolation, the energy incident at a place with atmospheric effects. I will, once I have obtained that value on the time versus insolation curve, let me mark the standard insolation of 1 kilowatt per meter square. So this same area I will achieve here by a rectangular component there, which is having a width of HAT or HAT minimum. Now this area which was HAT, for that width, equivalently the same number of hours, I will keep that width. The height I will keep it at standard insolation of 1 kilowatt per meter square, and I will achieve the same amount of energy, and that is which is in kilowatt hours. Now these two are equivalent as far as the energy is concerned. So I will use this particular concept. So let delta T, instead of being 10 minutes, I will make it equivalent to this time interval. So which is HAT minimum hours numerically. So let us say for Bangalore, if HAT minimum is around 4.58 kilowatt hour per meter square per day, this we know how to find. You can look back into the topic on week 3 and 4. So I will set delta T to a value which is less than 4.58 hours numerically. So let us say, for example, I will set it to around 4 hours. You can set it to still lesser hours also, but let me take this example of around 4 hours. So I know that in 4 hours time there is sufficient energy to provide 1000 liters, pump it into that one. So I will have to accordingly rate my other centrifugal pump and motor components. So let us see how much amount of hydraulic energy or hydraulic power is required. So let us say Q dot, which is Q by delta T. Now Q by delta T is 1000 liters by 4 hours, which will work out to be 0.0694 liters per second, and which is 0.07 into 10 to the power minus 3 meter cube per second. Now the discharge rate or the flow rate has come down drastically. So let me now make some space. Now all other parameters being same, I will expect you to go through the same sequence of calculation. I will now point out only the difference. Now you will see that here HF is calculated using the Darcy-Weisbach formula, F L by D into U square by 2G in meters. F is the friction factor. You will have to go through the same sequence of finding the Reynolds number, the roughness ratio. In this case, roughness ratio is 0, and then appropriately find F using the Colebrook equation. L and D is known, same values. U would have changed. The fluid velocity, because Q dot has significantly becomes low, U is Q dot by A. A has not changed, and therefore U would also proportionally reduce. U square would be still further less, and then this gives you 0.07 meters. The head loss due to friction is 0.07 meters, which is very small compared to the 18 meters that you saw in the earlier case. And the total dynamic head is around 8 meters. Compare this. In the earlier case, the significant amount of total dynamic head is contributed by HF due to friction loss. Here, the friction loss component is contributing very insignificantly, in fact negligibly. So almost the entire amount of head is due to the suction and the delivery head. Now what is the hydraulic power required? 1000 into 9.81 into Q dot into H. So if you plug in these values, H is 8 meters, Q dot as here, you will see that the power requirement is only 5.45 watts. Now this is dramatically low. Compare this with example 1, where we had calculated 425 watts, all parameters being same. The only thing is that we have made a change in Q dot, reducing the discharge rate, and then we have linked the discharge time to the insulation, so that basically the discharge, the flow into the overhead tank has been spread out through the whole day rather than just only 10 minutes, and that is why you see a very low hydraulic power requirement, because the flow has been spread out, the discharge has been spread out throughout the day instead of just only 10 minutes. That is the advantage that you can gain if you link it to the solar insolation. Let us now consider one more example. This time we will take a Borewell example. Let us say this is the ground level, and this is beneath the ground, and deep within the ground there is water available for us to put a deep pipe like this, and try to extract the water from deep within the bowels of the earth. Now let us put a submersible pump here. So this will be a submersible pump, motor and pump combination, and through a pipe you will be drawing out the water. So this is actually the delivery pipe. There is no suction pipe because the pump is submerged in the water, and this water is put into a storage sump here. So that is delivered here. This is at ground level. So there is some horizontal movement flow of water at ground level and then delivered into the pump, into this sump here. So this is a very typical borewell system, and let us take some typical depths. So around 600 feet. So 600 feet depth borewell is pretty common. So this entire depth is called the delivery head. There is no suction head. Then the water has to travel this horizontal distance in the pipe depending upon where the sump is located. And let me take a typical example of around 200 feet distance horizontal travel. And let us consider the dia of the pipe. Nowadays, people use PVC pipes, but steel pipes are also in use. Let me consider a steel pipe so that we will have some ratio of roughness to calculate. So the dia of the pipe is 4 inches. You also have 6 inches dia, and depending upon the amount of water that you need to discharge, one will choose the dia of the pipe. So this is the Borewell example, Borewell system that we will try to look at. One important thing is that the submersible pump, and when you take off some submersible pump, there is no suction head. Hs is equal to 0. Now Q, typically the discharge out of the borewell is the order of 100 liters in half a second, in half a minute. So which means 30 seconds. So this is the order of magnitude of the discharge that will be coming out of a typical borewell. But this is not a strict value. It depends upon the amount of water that is available, the depth to which the pump has been placed under the ground. So therefore, this is only a representative value, 100 liters in half a minute. Sometimes you have some borewells giving much more, and sometimes some borewells give less. So this dia of 4 inch boils down to 4 into 25.4 by 1000 to convert it into meter. Q dot, the discharge rate or the flow rate, is 100 liters in 30 seconds, which will give you 3.33 liters per second, which is 3.33 into 10 to the power of minus 3 meter cube per second. Hs is 0, Hd is 600 feet, which can be converted into meters by this conversion factor, 12 into 25.4 by 1000. So this works out to be 182.88 meters. So now the fluid velocity or the water velocity in the pipe is Q dot by A. So this 3.33 into 10 to the power of minus 3 meter cube per second by pi by 4 d square. So this is around 0.41 meter per second. So this from this we can now calculate the Reynolds number. So we follow the same process. So let us calculate the Reynolds number. UD by nu is the kinematic viscosity, 0.41 meters per second, 0.1016 meter, and 1 into 10 to the power of minus 6 meters square per second for the kinematic viscosity, which is equal to 41656, and that is the Reynolds number, which is much greater than 4000. Therefore the flow is turbulent, and you have to use the Colebrook-White formula. Epsilon, or the height of the surface bump, for steel it is 0.1 mm. So therefore the roughness ratio epsilon by d is 0.1 mm by 0.1016 meter. Converting it to mm by multiplying by 1000 will give you 0.01 as the roughness ratio. Now the friction factor, using the Colebrook function that we created, we give the Reynolds number and the roughness ratio, and then you will obtain the friction factor 0.024654, and the head due to the friction loss is F into L by D into U square by 2G, 0.51 meters. The total dynamic head is Hs plus Hd plus Hf, 0 plus 182.88 plus 0.51, which is 183.4 meters. Now you can calculate the hydraulic power, just 1000 rho into G to Q dot into H, which is 5991.2, roughly 6000 watts. So roughly 6000 watts of hydraulic power is needed to do this hydraulic work. So probably you may have to rate your motor pump combination at probably around 7.5 kilowatts or 10 kilowatts, depending upon the availability. So probably a 10 HP motor pump system can be used.